Okay, in the last class, we have learned about doing lifting analysis with API factors. So today, let's take a look at how to do it with the DNV factors. Now, when we look at a normal lifting offshore, so what happens? There will be a crane, there will be a hook point, and there will be rigging connected to the structure. So we will be having structure over here, and we will be having a rigging connected. And now when we do the lifting, we have different stages of lifting. So now when the cargo is in air, we call it load in air. And when the cargo is at sea level, we call it load in splash zone. Here, the dynamic activity would be more, and there will be lot of external loads acting on it due to water movement, and it can be slamming. Everything will be over there. And then next stage goes to load fully submerged, and then the final one is load at seabed. So now if you look at all these four cases, the maximum dynamic activity happens in load in splash zone. So when we do the analysis, if we do this one, this will be good enough to make sure that it is safer in all other cases. Now, while considering this case, there are some other factors also we need to consider. Now, first talk about the lift in uh, splash zone DAF itself. So if you look at DNV, there are different options. So if you want just air, there is a different calculation or different table to select for the DAFs or load in air. Now, if you're going for splash zone, what we have, there are two types of structures with the mud structures. So there will be a structure with the roof in top. So this is suction pile. Suction will have a roof at the top. So for structures with the roof at the top, it will be having um 1.65. So 1.65 is the value. DAF value is 1.65. And if the structure have a mat, so something like this, if the structure have a mat, what we have is DAF value is equal to 1.9. So this is 1.9 we are considering. Whereas if we are going to fully submerge, you can consider a DAF value of 2 as well. So some cases people used to take a conservative value of 2. And but there is some recommendation when you are taking 2, you should be using submerged weight factor. So there will be a reduction in the density due to the buoyancy effect. So the density will be reduced by 0.87 value. So that is a different story. So now consider I am going for a mat structure and I will have a DAF of 1.9. Then there is something called COG shift factor. So COG shift factor is like there is a chance that once we do the design and have the fabrication, the COG can shift anywhere between a certain range. So it can be 5% of the total dimension or 10% based on the conservative what the client is asking for. So at the moment I am just applying it 1.05, but there is a actual way to model the COG shift factor, COG shift, and do the analysis. So we will be doing analysis like this, so that we will be taking in the next few videos. We will be coming to this point. Now that is COG shift factor. So this one dynamic amplification where I told to account for the dynamic effects. Next one is weight contingency factor. So weight contingency factor is account for the increase in weight. After design stage, when we do the fabrication, there will be some weights which we were not accounted for. So there can be some increase in the weight of the final fabricated structure. So this value which will varies from different stage. So if you are in a very detailed engineering stage, maybe you can consider very conservative 20%, and fit stage. So come to detail stage, we can consider 10%, and if you are very closer to the as-built stage, we can consider maybe 5%. So it all depends. But understand what is weight contingency factor. Next one is consequence factor. Consequence factor is like something can go wrong and the structures can fail during the lifting, and this factor there are two factors, 1.3 and 1.15. So 1.3 is like for this paradise and the subsequent locations, and then 1.5 is the members connecting closer to it. So for the members farther from here, you don't want the consequence factor. But as a conservative side, and to make our analysis in a single step, we will consider a blanket factor of 1.3 for the structure, so that the structure will be superficial. Now if you, let's say, if you have some issue with the consequence factor, like this is like too much, and if you want to reduce the conservatism, then you can do it partially. You can do the factors, apply the factors partially, and do the analysis. Then coming to skew factor. So skew is an interesting concept. So in the next video, definitely we will be talking about the skew. So skew is nothing but, now let's say we have a structure, and we are connecting two slings diagonally and connecting the hook point at the center. Now I am going to lift it. So if the sling, so all my assumption is my COG point is matching with my geometric COG. So in that case, my slings and every angles will be same. So in the ideal case, what happens is, um, these two slings should take equal load. That means, let's say, sling 1 and sling 2 should take 50%, 50% each. But what happens is, due to some fabrication tolerance, there can be slight increase in one of the sling and slight reduction in one of the sling. So then what happens means, the shorter sling, so when we start loading, so we have two slings, one is shorter and one is longer, and when we start loading, the shorter one will be start getting loaded first, because it will be coming to tension sooner. So once it start getting loaded, and after a certain after it take a certain weight, the elongation will match with the other one, then only the other sling will take the load. So in that case, what happens is, the shorter sling will take more load than the longer sling at some point of time. So that difference, so let's say that difference in percentage is X percent. So sling 1 will take 50 plus X percent, and sling 2 will take 50 minus X percent. So in that case, what happens is, how we define the skew factor SKF is the increase in that percentage, 50 plus X by 50. So that is skew factor. Now let's say, uh, so here I am defining. So skew factor, DNV recommend is to have 1.25, but some people will recommend 1.5 for heavy structures. So this is very conservative. But now let's understand what happens if the skew is 1.25. So if the skew value is 1.25, the X, if you change this X is equal to skew factor into 50 minus 50. So you will get a factor of 12.5. So that means when you consider a skew factor of 1.25, you will get a split in the percentage load of sling 1 and sling 2 as 62.5 and 37.5. Now if you consider a skew factor of 1.5, if you do the calculation, you will get a difference of percentage as 75% and 25%. So this is the idea behind the skew. And now at the moment, for the initial analysis, what I am going to do is, I am going to apply this factor as a blanket factor. So I am not going to change any of this. Then now let me apply. So if I multiply all my factors, what I would get is 3.57. So for that, what I will do, I will come to my previous model, and here let me take a look at the load combination. So I have these two load combination which I gave for the API. So I can delete one of the load combination. So let me delete this one. I will have only LC1. So LC1, I will change the factor. So I will change the factor to 3.5. So let me take a look again. It was 3.57. 3.57. Now let me close it and I can do the analysis. So to do the analysis, let me come to static analysis with gap element. I will select my element check option, and here I can select my file. Yeah, now I can run my analysis. Okay, so I made a mistake. I didn't remove this LC2 selection from my data gen or the load case selection, so that I need to remove. So I can come to load combination. This one I need to remove. So this one is still there like a unknown. So let me see whether I can remove it from here. Okay. Okay, now it's gone. No, nothing is there. So I can run the analysis again. Okay, still showing some error. Okay, I will go to data gen and check. 1 minute. So in the data gen it was not updated, so I need to make sure that it is getting updated. So let me close the file. So it should be better if you close all the files before running. So I deleted the LC2 from data gen and let me run again. Okay, now it got run. So now here I can check my member properties and all. So if you want to see the UC, you can come over here, see the UC. So these are my uses. If I want to have a filter like let's say 0.6, let's see if there is any UC member over 0.6. Okay, so my pad I here is showing like it's failing. So that's not a desired one. What I would recommend is you can change the pad I. Maybe in the next video I will show you how to change it to make it safer. And here maybe we can do it here as well. So let me do that. Let me save this one as a new file. So here I am going to define a new section for pad I. I will put it like prismatic. So y dimension I will put for the width of the pad I, let's say 20 centimeter, and sorry, is the dimension, and y dimension is the thickness of the pad I, maybe 3 centimeters, so 30 mm. Okay, now I can just define my property. So I will come over here pad I will just change the section. So I will change it to general and I will change the section now. Okay, now if I look at, I have this pad I over here. Now I can do this alignment of the pad I. So maybe color I will change it so to make it better. Or so edit, let me change the color so that you can see it a better way. Okay, so now let me select the pad I, change the orientation to 45. Okay, it should be minus 45 over here. Minus 45. So this one, it should be minus 45. And this one should be 45 and other should be 45. 45. 45. Okay, now I can rerun my analysis and see how this one is coming. So to do that, let me change the naming. So I can change my member. Okay, now it got run. So I can check my result analysis. So result member UC. So maybe I will put 0.5. See, the UC also reduced. So now the structure is good. So you can see the member uses. So these are the member uses what we have. And if you want to check the plate UC, you can check the plate UC. So maximum plate UC is only 0.56. That's also good. And you can check the deflection shape. So this is the LZ1. Animate 30. So this is the deflection behavior. And if you want to have the sling property, axial tension load. So this is again it's in newtons. So if you want in kilonewtons, you can come over here, member in groups table. You select this, and you can see the sling tensions. So it's only in the local x-axis, not in y or z or any moments. That's why we gave our proper releases. And so this is how you check. Then you can compare it with the joint reaction. So joint reaction is said in LC1 should be equal to our actual LC1 loading. So for that you can check here whether this one is equal. So you can go to your member. So you can go to your member, load, display, and here you can check what was in the LC1 combination total load. So 548. So this one should match with our reactions. That is matching. The next most important one is the joint reactions. That should be very minimal. So for that you can check here joint reaction X 0 0 and joint reaction Y it's 0 0. So that our lift analysis, the analysis procedure is good, and this is how you do a lifting analysis with DNV factors. And next class we will be looking at how to do a skew analysis.